Hi everyone. There's been a couple times in prior years where people have just asked me to refresh them on the technique that I developed for factoring trinomials with leading coefficient not 1. And so I decided to make a video that I can put out there so that if you ever want to re-see it or kind of relearn it for yourself, you'll have the record there. So just to start, I'm going to kind of show how I springboard this in my classroom, and we start with leading coefficients at R1, or maybe if there is a leading coefficient, it probably divides out. And so we talk about you should divide out any common factors. In this case, there's a leading coefficient of 2, so we would divide the 2 out. And everything is divisible by 2. So then I end up with x squared plus 12x plus 27. And we talk about now I only need to worry about the part in parentheses. The 2 is just kind of coming along for the ride. It's the factor that stays out front. And when factoring trinomials with leading coefficient of 1, based on the property that we found when we were multiplying binomials that produce trinomials, we discovered that the constant term is the product of my two factors, and the two factors sum is the middle term. So I need two numbers now that multiply to be 27, add up to be 12, and as we know, those are going to be 3 and 9. And that's kind of how we deal with leading coefficients when we're first learning trinomials. Well, we just divide out the leading coefficient. Just so happens that everything divides by the leading coefficient in kind of the beginning cases. But the idea is, well, why can't we just always do that then? And that's essentially what the method that I teach in the class is founded in. So for example, let's say I have a 3 out front. Well, when there was a 2, I divided the 2 out. So let's do it even with a 3. So when I divide the 3 out, I then end up with x squared plus 16 thirds x plus 16 thirds. Now, similar situation. I need two numbers that are going to multiply to be 16 thirds, add up to be 16 thirds. So let's deal with the add up to be 16 thirds piece first. So if I were going to kind of start to construct my factors, I know that they're going to have to, well, these are both positive, so actually I know this is going to be a plus. It's going to look something like this, right? Because I know they have to add up to be 16 thirds. Now, that it could be 1 and 15 thirds, it could be 2 and 14, 3 and 13 thirds. I don't quite know, but I do know that they have to multiply to be 16 thirds, and this is kind of where we pause and we talk about, once I get my answer, how do I check and I know if it's right? Well, I would multiply it back through. Like in this case, I can multiply this back through, and I would see I get the original result. Well, if I start to multiply this one back through, I would at some point be multiplying thirds and thirds to get my last term. But thirds and thirds make ninths, and this last term is not in terms of ninths, so I really need to rescale it if I'm going to be able to find the factors. So this is going to be x squared plus 16 thirds x plus multiplying this by 3 and this by 3 to make my ninths. That'll be 48 ninths. Now I need two numbers that multiply to be 48 ninths, add up to be 16 thirds, but my thirds and my ninths were really already taken into account when I constructed these factors down below, so I really just need to worry about the numerators. I need two numbers who multiply to be 48 ninths, add up to be 16 thirds, but I really just need the 16 and the 48, and I find that that's really 12 and 4 are the numbers that I'm looking for. So I have 4 thirds, 12 thirds. Let's check and see if they do it right. 4 thirds plus 12 thirds is 16 thirds. And 4 thirds times 12 thirds is 48 ninths. And they do the job. If you've ever taught factor by grouping or factor by bottoms up, this adjustment right here is why mathematically you are multiplying the leading coefficient by that last term when searching for the two numbers to split up the middle term. So they check out. Now I just simplify my answer. 3x plus 4 thirds. 4 thirds won't simplify, but 12 thirds is really the number 4. And you have it factored. And if this is actually a solve by factoring situation, you actually are in a better situation than when you would factor by other methods, because I can just look and see the roots right off the bat. The roots are -4, -4 thirds. Whereas when I tell students when we're first learning this, you might want to multiply this 3 through in order to get an answer that checks with the book. You'll get 3x plus 4 and x plus 4. The slight downside of this method is I don't see exactly what the root is right off the bat until I've kind of solved a couple and recognized the pattern, seeing that this is really going to be -4 thirds. Whereas this one, they kind of stare at you, very similar to the situation where these roots stare at you. So that's why it's called factoring for roots. That's how I teach it in my honors class. And we spend the next day then practicing doing them mentally, juggling the factors in our heads so that you maybe can become quicker and more efficient with it. But a lot of students still rely on the factor by roots method, where you have to kind of deal with fractions. I will say, I even use this in my algebra class, but I kind of use a table to keep the items more organized. So I'll demonstrate how that works. So again, start out, divide the leading coefficient out. I get 6 x squared plus 13 6 x minus 5 6. When we made these tables before, when multiplying binomials, we always found that this x squared was up here. These were the x's. And then this was the constant term down in the bottom right. So I see actually, again, I have to multiply to be negative 5, 6, add up to be 13, 6. I see that these pieces are really going to be 6 and 6. Or I'll even write the word out, 6 and 6. It just depends on your preference. But I kind of construct the table here and say, okay, so hey, look at this. If I were to check this out, 6 and 6, this is going to multiply to be 36. So this last term needs to be rescaled. And they pick it up pretty quickly. It needs to be multiplied by 6 and 6 on bottom. So it's got to be x squared plus 13 6x minus 36. That's what's going to justify when I actually find my factors. They're going to have 6 and 6 in them. Now I need two numbers that multiply to be negative 36, add up to be 13 6. And I search and I find that those two factors are going to be 15 6 and negative 2 6 to make the negative 36. And then we check it out. 15 6 plus negative 2 6 is positive 13 6. 15 6 times negative 2 6 is negative 36. So they work out. So plus 15 6 minus 2 6. And if this was equal to 0, I'd actually be done. I'd have the roots. It'd be positive 2 6 or 1/3, negative 15 6, which is negative 2.5. If they want to check their answer, if this was just factoring, I would maybe say, let's simplify these. And when I simplify these, divide the top and bottom by 2, or by 3, I get 5 halves. Divide 2 6 again by 3 on top and bottom, I get 1/3. So I see, similar to the last case, where this one that didn't simplify because it has a denominator of 3 needs a 3 to multiply through. This first one needs a 2 and this needs a 3, but luckily that's exactly what the number 6 is. So this is a good chance for you to kind of discuss the commutative property of multiplication. Since this is a chain of 4 multiply pieces, I can move them around, and I will keep the 2 in front of the first one, so that can distribute through. And then I will use the 3 on the second one to distribute that through, and end up producing 2x plus 5 on the first, and 3x minus 1 on the second, if this was just a purely factor and they wanted to check it in the book that uses non-fraction answers. So there's benefits to leaving it, though, in this factored form because you just see what the roots are. They're staring right at you. Positive 1/3, negative 5 halves. And that's the technique that I use. I think the benefits are that it conceptually ties back to a similar situation. It doesn't require a different method for different scenarios. If it's a leading coefficient of 1, you use the whole multiply add bit. If it's leading coefficient not 1, then they're doing either factor by grouping or bottoms up. It disconnects the topics when they really should be the same. And lastly, it doesn't require any tricks. It's based in logical steps that kind of all tie back together, which I think is really a good goal of math. Once you kind of tell them that it's a magic trick that you're doing, you've lost them, and you've kind of lost really the meaning of math, I think, in school, which is to be the logical foundation of thinking. So there's the method. Hopefully this maybe provides some help, and thank you very much.